Okay, so I want to show, and this will just be a real quick video, just kind of a demonstration of why side-side angle is called the ambiguous case. And so I found this GeoGebra kind of interactive activity, and I'll go ahead and share the link too with this, or you could see it from the screen as well. But again, here's something where you might be given two sides in a non-included angle. And so, the side length B is here in blue. There's nothing special about 9. You can make it, you could slide that to make it longer or shorter or whatever, it doesn't really matter. And then angle A is just a default of 30. We could kind of change that. And then our opposite side here, 3. And you can see right away, like, like if you pick this missing angle, this missing side, which is opposite the angle that you're given, right? You're in a side-side angle case. If this side is too short, no matter what, no matter what you do, it's not going to reach the opposite side of our triangle. It's not even going to create a triangle. So this is a case where I could give you 3 fictitious pieces of information and no triangle exists. So I can maybe make this shorter, and we're still not there yet. And if I make this angle small enough, eventually it would reach, right? And you saw glimpses of like 2 triangles showing up or 1 triangle showing up, and so we'll look at that too. But like if it's not in the right ratio, it's not gonna make a triangle. Okay, so now let's see what happens if we make this side length long enough. So I'm gonna just adjust this a bit, just have a good aesthetic here. So if A is long enough, it actually can intersect it in 2 different spots. And so there's a darker blue triangle, so A to C to B1, and both of that dark blue triangle has an angle of 31 degrees, a side length of 9, and B1C, this length right here, of 5.3. But notice that if that 5.3 swung around and opened up angle C just a little bit bigger, there's a second triangle, A C to B2. Both of those triangles have the same 3 given pieces of information. They both have an angle of 31. They both have a side length of 9. And then they both have a side length segment of 5.3. So if this segment here is long enough to intersect that baseline, it potentially could create 2 triangles. And it's really just an arc. So wherever it crosses that line, that's where those 2 triangles exist. Now, I can make this bigger, and it makes, bigger, and it makes the darker blue one kind of start to get really skinny and very, very obviously scalene. But if all of a sudden I make that too big, if all of a sudden this, right now it's 7.2, if 7.2 gets bigger than 9, watch what happens. By the time it swings over here, it's gone past the 31 degrees. If that is too big, that's bigger than the given value of 9, I can't get 2 possible triangles. I only get 1. And so, the ambiguous case shows that there could be 0 triangles, 1 triangle, or 2. And it all depends on how big is the side that's opposite this given angle. If that side is too small, it might not even make a triangle. If it's bigger than 9, right? If it's bigger than the second, the other given, it's only gonna make 1 long, obtuse looking triangle. But if it's somewhere in the middle, in that sweet spot, where it could arc and give you like 2 intersections before it crosses back over here, there are 2 possible triangles. And again, that's going back to thinking about geometry, like, why do we never use side-side angle? And like when I used to teach honors geometry to freshmen, I would say, oh, how silly, we can't say bad words in geometry and accidentally call it backwards. But the reason we can't use it is because we don't know which triangle we're talking about. Are you talking about like the darker blue one that is off here on the left, or are you talking about the large one because both of them, like the large one, meaning it's like the dark blue plus the light blue together, both of them together form a triangle, has the same three given pieces of information. This B being 9, this A being 6, and the angle opposite being 31 degrees. So I like that visualization. And again, I'll share this exact link on GeoGebra. That was great. Jerome A. White. Thank you for creating that ambiguous case activity. Okay, so I'm hoping that visualization helps. But remember, when you're solving law of sines and you're in that ambiguous case, anytime you're introducing the inverse sine function, that should be an indication that, wait a minute, I have a couple possible things that could be happening. I could get a sine ratio that is bigger than 1, and that would mean that I've got no triangle. I could get it equal to a value that gives just one triangle, or I could have it just enough right information so there are exactly 2 triangles. Okay, so hope that video helped, and then we'll go through some more examples and start looking at law of cosines.